Right, this is part 2 of the SAT solving lecture, and what we're going to do in this part is we're going to look at using the DPLL algorithm ultimately on a computer to solve a practical problem, well, a sort of practical problem, and that problem is solving sudoku puzzles. So it's using DPLL, so using a SAT solver, but we're going to use the DPLL algorithm. So using DPLL to solve sudoku. So let me first remind you what a sudoku puzzle looks like. In order to be able to draw things on the tablet here, I'm going to deal with a small puzzle for illustrative purposes. So I'm going to, rather than the usual 9 by 9 square that one gets for sudoku puzzles in books of sudoku problems, I'm going to use a 4 by 4 square, which makes it a very, very easy problem. But when we come to the computer solving, we're going to go to 9 by 9 puzzles, the usual challenges that are in the puzzle books. So a sudoku, and the 4 times 4 version, is a 4 times 4 grid. That's a square with 16 cells in it, 4 times 4 cells. So let's draw those cells. So divide down here. Ooh, they're getting a bit wiggly, but never mind. Ooh, very wiggly. Right, but it's not just divided into 16 cells like that, but the line down the middle here, both of that vertical line down the middle and the horizontal line down the middle are thick lines. Maybe I should do that properly. So if we go to the pen settings and we go to the pen width, let's put a proper thick line in there. So still looks very messy, but never mind, it's good enough. Let's set this back so we've got a decent pen width. Oops. That's still a bit too thick. I think this one is the one we want. Yeah. Let's rub those two off. Right. So a sudoku puzzle is in this case, a 4 by 4 grid, where some of the cells have numbers in. So I'm going to put 1, 2, 3, and 4 on the diagonal, and also a 2 in this square. The goal of the puzzle is to fill in every empty square with one of the numbers 1, 2, 3, or 4. And you need to do this in such a way that each row contains exactly one of every number 1, 2, 3, and 4. So no number appears twice in a row. Each column contains exactly one of the numbers 1, 2, 3, and 4 as well. And each of these corner squares, so these 2 by 2 squares at the corners, also contains exactly one of the numbers 1, 2, 3, and 4. And if you try to solve this problem yourself, it should not take very long. For example, one can begin with the observation that we need to complete this square. 1, 2, 3, and 4 need to go in this square. But this cannot be 2 because then we would have 2 2s in this column. So this has to be 1 and this has to be 2, and then from there you can continue with similar kinds of reasoning. Well, we've got the 1 here, so this would have to be a 4, and so on, and it's very, very easy to solve this problem. But as those of you who have solved Sudoku puzzles in puzzle books will know, the kind of 3x3 puzzles you can get in puzzle books, well, they can have different difficulty levels, but the hardest ones can be very hard indeed. You don't get that much information, and it's quite hard to work out how to find the solution. The first thing I want to show you here is how we can code up the Sudoku puzzle as a satisfiability problem. So let's give ourselves, go to a fresh page. Right, so we're going to code it up as a satisfiability problem. So we give ourselves a vocabulary of propositional atoms, or variables, as I'm going to continue calling them from the first half of the lecture. So we give ourselves a vocabulary of propositional variables that are going to encode an aspect of the problem. So I'm going to put in, I'm going to have variables. I'm going to use the following notation. So my variable, that should be an R, variables are going to be P, just so it's not just a number, and that's going to be P followed by 3 numbers, X, Y, and Z. So P, X, Y, Z is a variable name, and we're going to say this means row X let's delete that. Row X, column Y, so the cell in row X, column Y contains Z. So for my 4x4 puzzle, we've got 4 rows, 4 columns, and 4 numbers we can put in. So we have propositional variables P, X, Y, Z as long for every possibility for X, Y, and Z. Each of those can be any number from the set 1, 2, 3, and 4. So we have 4 times 4 times 4, 4 cubed, that's 64 propositional variables. In the case that we were dealing with a 9 times 9 puzzle, we would have 9 cubed propositional variables, which is quite a lot more. So using these propositional variables, we want to express clauses that when we want a formula in conjunctive normal form that any satisfying assignment for the formula will, through its truth values, the P, X, Y, Z that it's assigned true will tell us which cells to put which numbers in. So to do that, we're going to set up some clauses expressing the constraints that we have in a Sudoku puzzle. So the first clause I'm going to add is I'm going to add a clause saying that for every cell in the puzzle, we have at least one number in the cell. So each cell in the puzzle is pxy for some xy. And we want to say cell xy, cell in row x, column y, contains the number 1, or it contains the number 2, or it contains the number 3, or it contains the number 4. So we want to have pxy1 or pxy2 or pxy3 or pxy4. So that's a clause. And we want to have one such clause for every possible pair of values xy. So one for each of the, in this case, 16 cells. So we include such a clause for any pair of xy taken from the set of possible rows and columns. So taken from the set 1 to 4. Right, so that's altogether 16 clauses we've added so far, one for each cell. And each clause has 4 literals in it, positive literals consisting of the propositional variables. So we've said we want at least one number in each square, but we also want to say we've got at most one number in each square. We don't want to have 2 different numbers in the same square. So we can do that by saying that we're going to say that so for every pair of different numbers, m and n, we're going to say that the square xy cannot take both the values m and n. So we can say that by saying either the square at xy is not m, or the square at xy is not m. Oh, sorry, there should be a p here. Maybe I can do that. So not p x, y, n. So we want one of these for all possibilities for x, y, m, and n from 1 to 4. So for every square and every possible value of m and n, we want such a thing as long as n is different from n. The point is, for different values we can put in the squares, we want to say that it's not the case that the square has both those values. Right, now we want to do similar things for rows and columns. So for every row, we want to say that for every row and every number, we want to say the number occurs in that row. So it must occur in one of the cells in one of the columns in that row. So for that, we're going to say that if we have for any number that we want to put in the row n, and if we're looking at row x, it needs to appear in one of the columns for row that intersects with row x. So we can say that by for every row x and column n, and number n, we're going to say that either p x1, so either the cell in column 1 in row x has value n, or the cell in column 2 in row x has value n, so p x2 n, or the cell in column 3 has value n, so p 3n, or the cell in column 4. That's value n. So px 4n. And this is, of course, for every x, so for every row, and every number that we're considering that must appear in the row. Let me just delete that. So for every x and every n. Taking values from 1 to 4. So again, every row must for every row and number, the row must contain the number, and once again it can only contain the number once. So just like this row, we're again going to say that by if we have two different columns, then the row and any given number, then the row and then in the row x, the cells in the two different columns cannot both contain the same number. So let's call the two different columns y and y prime. So we're going to say for a particular row x and a particular number n, then n cannot be both in column y and in column y prime. So it's not the case that p x y prime n as well. And like the second clause here, we want one of these for every x, y prime, and n. So one such clause for every possibility of these, where these are in 1 to 4. No, sorry, this should be y, and y, the columns are different. So I should say, as I've written this clause and this clause, there's actually a bit of redundancy, because I'm saying, so for example, if we've got row 1 and number 1, so x is 1 and n is 1, so we will have one clause saying that 1 does not appear both in the column y equals 2 and the column y prime equals 3, but the way I've written it will have another clause that says that 1, the number 1, does not appear in row 1 both in column 3 and in column 2. So we have one version for y equals 2 and y prime equals 3, and another version for y equals 3 and y prime equals 2. It's clear that there's redundancy there, so we could actually probably better say that m is strictly less than n here, and that y is strictly less than y prime. Okay, so far we've said each number appears, so each square contains at least one number, and it doesn't contain two different numbers. Similarly, each row contains at least one number, and it does not contain two different numbers. And so we also want to say, so I'm not going to bother to write out the full clauses, we also want to say every column contains, well, at least one number and not two different numbers, so it's two different sets of clauses, but let's just summarize it more briefly by saying every column contains each number exactly once. I'll just say each number once. And we also, there's another constraint, which is that also those corner 2 times 2 squares also contain each number exactly once. So again, one can formulate those in much the same way. Again, we've got 4 squares in the corner 2 by 2 squares. So we also want, again, 2 sets of clauses that between them say that every corner two times 2 square contains each number once. See if I can make that neater. Each number okay, and I'll leave it to you to write these two out, as each one of them again should be 2 sets of conjunctions of clauses. So much in the same way that this was a conjunction of clauses, one for each pair xn, and this was a conjunction of clauses, one for each quadruple of x, y, y prime, and n with, well, in the end we decided it was best with y is strictly less than y prime. So the same for these, a conjunction of 2 sets of conjunctions of clauses. So we've got 2 sets of conjunctions of clauses here. And now we've expressed all the general constraints of the sudoku problem, but we also need the constraints for the specific problem we're solving. So if we go back to the one we've got, we can see we've got 1, 2, 3, and 4 on the diagonal, and we've got this 2 in row 1, column 3. So we can add that information as a clause here. So we'll add that information as a clause. So simply we need to add that. So this, sorry, that's not as one clause, but it's a conjunction of unit clauses, because it's we need to say this information, the 1 is in square 1, is in the top left square, 2 is in the square at, the number 2 is in the square in row 2, column 2, and so on. So that information is a conjunction of unit clauses. So we have the 1 is in, for this particular puzzle, the number 1 is in row 1, column 1 in that square, and the number 2 is in row 2, column 2. So in row 2, column 2, we have the number 2, and in row 3, column 3, delete that, let's try a 3, column 3, we have the number 3, and in row 4, column 4, we have the number 4. And finally, we had the one additional number which was in row 1, column 3, we had the number 2. So in row 1, column 3, we had the number 2. And we can submit that to a SAT solver, and when we get a solution, it will tell us which variable, by the truth values of the variables, we look at which ones have been assigned true, and from that we will get which numbers to put in which cells for a solution of the problem. So in this case, let's look at some quantities associated with this problem. So for the 4 times 4 sudoku, we have we have 4 cubed, that's 64 variables. And we have 448 clauses in total if we do the more efficient version where we only consider the y being strictly less than the y prime and so on, so we don't duplicate the same pairs of constraints in a different order, so as I already mentioned. So in that case we have 448 clauses. Whoops. 448 clauses expressing the general constraints for the sudoku, for an arbitrary 4 times 4 sudoku problem. Plus we have the unit clauses that have the specific information about which cells have already been filled at the start of the problem. So in the case we were looking at, that was 5, because there were 5 cells filled. So this is the number of clauses that appear in the conjunctive normal form that we're going to submit to a set solver. So let me put that in brackets because this depends on the problem. But we always have the 448 common clauses. In fact, you can think about it for yourselves. Some of the clauses we've included are redundant. For example, we don't need to always say that, so for each notion, like a cell, a row, a column, and a corner square, we were saying it must contain at least one of the numbers and it cannot contain 2 different such numbers. In fact, you don't need to say that for every concept once you've said it. For some of the concepts, some of that information is redundant. So it is possible to find more efficient sets of clauses if one wants to reduce the number of clauses. But actually doing that does not help set solving, because it's better for the algorithm to have more clauses in some ways, and this turns out to be better in practice in this case, because the more clauses you have, this is not generally true, it's not always true, and sometimes you need to be a bit careful how you code up a problem. But in this case, if we have all 448 clauses, it turns out that this guides the DPLL algorithm better than if we'd reduced it to many fewer clauses. I think the minimum number of clauses we can get away with instead of 448 for a 4 times 4 sudoku is well, according to my calculation, 144. But anyway, as I say, it's more efficient actually to include all the clauses, or it seems to be, at least. Okay, so suppose we were going to do the same thing for a real sudoku, like a 9 times 9 sudoku. So for a 9 times 9 sudoku, it turns out things get a lot bigger. So now we have 9 cubed variables. So whereas 4 cubed is 64. I don't remember exactly what 9 cubed is, but it's in the high 700s, I think. So 9 cubed variables. And in this case, we have 11,988 clauses expressing the general constraints plus the number of initial values. So let's write that. Hash for number of initial values. So initial. So we have this many clauses. So that's quite a large number. So what I want to do now is briefly show you this working in practice, and we'll do that for my implementation of the DPLL algorithm. So we're not going to use a fancy SAT solver, but we're going to use an implementation of the DPLL algorithm that I wrote in Haskell, in the programming language Haskell, which is a nice functional programming language. I don't know how many of you have experience of it. So let me go to here, I think. Right, so here we're in my Haskell implementation folder. So what I want to do is load up, well, what I implemented, if we look inside the folder, so there are various DPLL files, but the one of particular interest is full DPLL, because this implements the full DPLL algorithm. The simple DPLL just does unit clause propagation and doesn't deal with the pure literals. So I'm going to use the full DPLL algorithm, and but this is just the algorithm itself. So I want my wrapper. I want to use my wrapper program, which is going to deal with the sudoku problems. So let's go to Haskell. I'm going to use it in interactive mode, so that it's nice and convenient to work with. It would be faster if I compiled it, as that the interactive mode is interpreting the program rather than compiling it. But still, it's going to be fast enough for our purposes. So I'm going to say GCHI, the Glasgow Haskell compiler in interactive mode. I'm going to give an option that I don't want certain warnings, because Haskell is very fussy. In my program code, I put in some tabs instead of using multiple spaces, and Haskell will complain about that. It doesn't like tabs. It's not really important, but I don't want to see silly warnings about using tabs instead of spaces. And okay, let's just do that, and that will run Haskell. So we're now in the prelude, which is just the general library available with Haskell. I want to load up the module that I've written, which is the sudoku file. So that :L means load. I'm going to load sudoku well, I misspelt it. That's not a good start. So let's get back to that and go and change the S to a D. There we are. Right, well, it says compiling. I think that just means loading, because it does say that it's interpreting it rather than running a compiled version. I don't really care what's going on behind the scenes. What I want to do is use it. So let's have a look at the code, sudoku.hs, and see what's in the file. So I've got it in an editor window here, an Emacs window. So here I'm importing my DPLL algorithm solver, and I'm giving myself some notation for formulas. So I want to use the same notation that I'm using in the lectures. So I'm going to use P plus an X, Y, and an N for row X, column Y, and number N. And here I set something called the sudoku root, which is the square root of the number of cells we have in a row or in a column. So we were dealing with 4 times 4 sudoku before, so the sudoku root should actually be set to 2. And the reason I use the square root is because sudoku problems, a general sudoku problem, only makes sense for an n by n square where n is a square number. Then you can, because then if it's a square number, you can divide it into the mini squares that in the 2 by 2 case we had as corner squares. So for a 9 times 9 problem, the sudoku root would be 3, and kk here is then the number of cells we have in a row or in a column, which is 9, 3 times 3. So actually I want to change this value to 2, because I want to deal with the problem that we had, that we were looking at before, the very simple sudoku that is really easy to solve, but let's still look at that. So let's set that to 2, and I'm going to save that. So now I actually need, so at the moment if I look at kk, we see it's 9. So I need to load again. So loading it again, we should now see that kk, so the second one's a capital letter, right, kk is 4. And if we go down, then we see we've got some example sudoku problems here, and this in particular is the one that I had in the lecture. So this is saying, so this is the 4 by 4 sudoku problem that in row 1, column 1 has number 1, in row 2, column 2 has number 2, in row 3, column 3 has number 3, row 4, column 4 has number 4, and in row 1, column 3, so remember the other cell off the diagonal, row 1, column 3, we have 2. And I can solve this by just saying solve, and what I want to solve is lecture. Well, just check the value of lecture, right, so there we are. Lecture is that data, and I've got this solve function here, which converts this into a propositional formula, and then gives it to the DPLL solver, and then if it gets a solution, prints the solution out in a nice readable sudoku form. So if I solve lecture, you'll see it will take no time at all, because it's such an easy problem. There we are. So we instantly get back the answer. This is the first row. So we've got the 1 and 2 that were given, and 4 and 3 are being filled in the second column and the fourth column. This is the second row, 3, 2, 4, 1. The third row, 4, 1, 3, 2. And the fourth row, 2, 3, 1, 4. I could go back to the puzzle as I originally wrote it and fill these numbers in, and we could check that it really is a solution to the sudoku problem, but I'll let you do that for yourself. What's more interesting is to look at the work that's being done behind the scenes here. So when I ask, maybe I'll close this window, when I ask to solve, then, so initial was a list of triples where these triples are giving the data of the data of the values that are given to us before we solve the problem. So we saw that, we saw what the list of triples was with these 5 entries for our simple problem. So what we do first is we convert that to a formula in conjunctive normal form. So CNF is my variable for the formula that we get in conjunctive normal form, and that's done using this function here, which is written in rather concise Haskell notation. But basically, what it does is it takes what's called the base, and these are the general constraints that apply to any 4x4 Sudoku problem. So this is going to be the 448 clauses you already have, and so that's considered as a conjunctive normal form, which is a list of clauses, and we add to that list, we concatenate to that list the list of clauses, of unit clauses we get by just converting each of our initial data points into the unit clause that expresses that particular row in that particular column, the cell in that place, has the number n. So that is how we convert it to a formula. Once we've got our formula, then our solution, this is like a possible solution, is we apply the DPLL algorithm, which is written in my full DPLL file. I'm not going to show you the code for that, or maybe I will very briefly, just so you can see what sort of size it is. But I think, given that your homework is to write your own SAT solver, it's probably better not to show you that code. So actually I won't do that. But anyway, we apply the DPLL algorithm to the conjunctive normal form, and that gives us either nothing or a solution. So the nothing means we don't have a solution, the formula is not satisfiable because DPLL is a complete algorithm. Or alternatively, we get a value, and that value means we've got a solution, and we convert that. We know that we're dealing with a Sudoku problem in this case because this file is about dealing with a Sudoku problem, so we convert that into a printable form where we print it as a list of lists where each list is a row, in one row of the solution with its entries, as we saw in the printed solution that we had when we ran the Haskell program. One other thing to mention is how this Sudoku base is constructed. So this is basically a value that depends on the number k here. So the number k you'll remember is the number of cells in a row or in a column, and it's also the number of different numbers we have for filling that we can put in the cells when we're solving the Sudoku. And the Sudoku base is exactly this lot of conjunctions of clauses, where we have a conjunction of clauses expressing at least one number in each square, a conjunction of clauses expressing every number appears in each row, every number appears in each column, every number appears in each mini square. So I've got them in a slightly different order, so that's at least one number. So, well, that's exactly what it says here. And then we've got the various conjunctions of clauses expressing at most one number in each square and so on. So that's coding up that information in such a way that it depends on the size of the Sudoku problem. As I said, in the case that kk is 4, that we have a 4x4 Sudoku problem, the Sudoku base is going to have 448 clauses. In the case that it's a 9 times 9 problem, then we have 11,988 clauses in Sudoku root. And if we go up to a 16 by 16 problem, it would be many, many more, but we're not going to consider that. So let's have a look. So here was our lecture problem. The other problems are all 9 by 9 problems, and they're taken from a particular sudoku puzzle book, an actual one that was bought from a stationery shop. So this is Jepni Sudoku, Pocket Sudoku, and we've got problem 1, a problem 2, and for those of you who've looked at, so they're taken from 2 different sources. So one is from the Pocket Sudoku, and another one is from Crosswords and Puzzles, Sudoku, and so we've got problem 1, problem 2, and often when you get Sudoku problem books, then the problems have different levels of difficulty. So this one's a very easy one, Zelolachek. This one is an easy one, and then there's medium level and difficult level, and at least in the book that I had, it goes up to a very difficult level. So here we're giving ourselves one that was classified as a very difficult one. And once again, you can read off this. So we've now got 9 by 9 Sudoku problem. I'm not going to actually write this out, but you can write it out if you feel so minded to do so. So here it's a 9 by 9 one. There are, I think, 24 different cells that have been filled in the initial problem, if I counted them right. So the first value that's in the problem that gets set to you is in row 1, column 9. So in the top right corner we have the value 7. In row 2, column 1 we have the value 7 as well. In row 2, column 3 we have the value 5, and so on for these, I think, 24 different values. And then we can submit this to the Sudoku solver. So let's do that. In order to do that, I need to change my Sudoku root back to 3 because these are 9 by 9 problems. So let's change that back to 3. My 3 key doesn't work, so let's use this virtual keyboard here. Set that back to 3. I'll save. Now we'll load up. Go back to Haskell. So I want to load again. Okay, so it loaded. Let's again look at the KK value. That's now 9. So let's see if it's going to solve the 3 by 3 problem. Let's give it the very hard one. So I want to do solve, and let's see what the very hard one. So it's problem 36. Let's just check that. Let's look at problem 36. So if you want to, you can draw a 9 by 9 grid yourself, go through these values, put them into the grid and try to solve this Sudoku problem if you feel like it. Let's have a... Oh. Okay, that should have been 36, not 39. That variable was not in scope. Problem 36 should be in scope. There we are. So those are the initial values. And now let's solve the Sudoku problem. I want to solve that variable. And there we go. So I've submitted it to the solver, and you see it's not giving us an instant answer in this case. So the DPLL algorithm is doing some work. Is it actually? It has given us a solution. So very good. So the DPLL algorithm, even though it's an old algorithm from the 60s and no competitor to modern SAT solvers, is still managing to work with a problem that has a number of variables in the 700s, and it's actually the number of clauses is over 12,000 in this case, because once we add the 24 unit clauses to the general 11,988 clauses, we get 12,012 clauses. So it's managed to solve a very difficult problem. Maybe we could have a look at the very easy problem, the Zelolachek one. So let's have a look, just check we've got that value. So problem 5. Yep, we've got that. You see it has a few more One way in which it's easier is that it's got more initial values in it, just a few more. But anyway, it's a problem that's much easier to solve by hand for a human. So let's solve that. So let's go back to there and put a solve in front of it. And well, it's a much easier problem for a human, but DPLL still needs to think about it. So it's interesting that, well, there we are. We've got a solution. Of course, I could time it to check whether it's really quicker or not. It seemed perhaps just a tiny bit quicker, but it's really hard to tell unless you time it. It's not really that interesting to know that. The perhaps interesting thing to observe is that it did not seem to be that much quicker for the DPLL algorithm to solve it. But nonetheless, these sudoku problems that one gets in sudoku puzzle books are amenable to even quite a simple set-solving algorithm. That's the DPLL algorithm. I want to show you one other thing before we finish. I'm going to quit Haskell and have a look at the files in here. And we'll see that we've got some sudoku problems in text files. Let's look at the hard one. So we'll look at sudoku hard, the text file here. And this is the same problem as specified here, but given as a conjunctive normal form in the standard input format for conjunctive normal form files, which is called Dymax format, and this is the format that you need to deal with in your homework. So in Dymax format, you can start the file with some comments. That's what the C is. So I'm saying this is the 9x9 sudoku puzzle, which is the very hard level in a puzzle book from the lecture. But in Dymax format, variables are just represented as positive numbers. So the variable p, x, y, n, where x, y, and n are numbers between 1 and 9, the natural way to convert that into just a positive number is to read it, well, subtract 1 from each of the numbers and then consider them as digits in base 9 notation, and then add 1 to the value because we want to start our counting at 1 rather than at 0. If you work out what that is, well, it's given by this formula. So n is our unit value, y is our what would be in the tens if it was base 10, but it's base 9, and this is our 9 squared. So because we're subtracting 1 from x, y, and n to consider them as digits, it's actually 81 times x minus 1 plus 9 times y minus 1. Then it would be plus n minus 1, but then plus the 1 in order to shift away from 0. So this formula gives us, in the end, a way of coding x, y, and n in the minimum number of values you can use for that, which is 9 cubed, which here is what 9, so it's not the high 700s, it's the low 700s, but anyway, it's 729 values. And so this is saying we are giving a formula in conjunctive normal form. It has 729 variables in it, so those are numbered from 1 through to 729, and this is our way of understanding what they mean. So if we use the inverse formula to this, we can view any such variable as a p, x, y, n variable. And in this case, we've got 12,012 clauses. So that's the 11,988 clauses we've got expressing the general constraints of a 9x9 sudoku puzzle, plus the 24 unit clauses that we need to express this particular puzzle set with this that's in problem 36 in this list of problems here in the Haskell file. So if we look down this, we see that I'm going to scroll down. So here we're starting off with all the unit clauses. So variable 79 is true, variable 88 is true, variable 104 is true. This is going to give the DPLL algorithm a very good start, because we can start off by doing a lot of simplification with these 24 clauses. Anyway, if you scroll down, we have the unit clauses, and then we have the non-unit clauses. So we've got we've got 1 or 2 or 3 or 4 or 5 or 6 or 7 or 8 or 9, and the 0 says that's the end of a clause. So it's that clause and 10 or 11 or 12 or 13 or 14 or 15. And if we go down, we see lots and lots of clauses with positive variables in. So this means all these variables are occurring positively, they're not negated. And in fact, in our long clauses, that was always the case, that the variables were not negated. And each of these clauses has 9 entries, because that was kind of how the clauses were set up. They would have the same number of literals in it, and in this case they're all positive variables, as the number of cells we have in a row. So still going down these positive clauses, I don't know how far I'm going to have to go before I get to negative clauses. And the negative clauses all occurred in clauses that had just 2 negated variables in, so we should start to see at some point, I should set up some faster scroll on this, here we are, the negative clauses then start to come in, and so indeed these clauses are all disjunctions of 2 negated variables. Anyway, I could go down to the bottom, but that's, I think, enough. The point of this was to illustrate the DIMAX format, which is going to be the standard input format for the homework, and this is how the DIMAX format encodes the conjunctive normal form that is the sudoku that expresses this sudoku problem 36, this very hard problem. One other thing I want to show you is how the solution is represented in the format that's required of the homework. So let's again look at sudoku hard, but I've got the solution in another text file, and we see the solution is in just some arbitrary order, just a list of numbers and negated numbers. And this says variable 513 is false, variable 675 is true, variable 512 is true, variable 558 is true, variable 720 is false, and so on. And if we go all the way to the end of that file, well, there we are. I mean, it's not very readable, so it was nice that this was converted in our printout into just knowing that it's a sudoku puzzle, into a square of solutions that we had. Just the information of which digit appears in each row. But nonetheless, this is the output. This format of output is the output that your homework solutions are expected to be in. Right, well, I think I've said everything I want to say, so I'm going to stop the video, and that is the end of the week. Well, I suppose it's the 4th week of semester, but the 3rd lecture of the course on SAT solving. Okay, so goodbye, and I guess we'll definitely be doing video lectures next week, and after that we'll see what happens. Okay, so bye for now, and if you have any questions on the material, please just drop me an email. Okay, bye.